Before we restart, some reminder, tomorrow the test is at 11:15 sharp. It will last, the test itself 15 minutes, there'll be probably 5 to 10 minutes of instructions at the beginning, so you should count on about 25 minutes where you have to be there. Let me come back to one slide where there is a bug. This one here, so the interfaces here were incorrect, so I've corrected them. They will be corrected on the version that will be put online after the course. But one thing I want to show here is that if you look at IPv4 address, every interface has one IPv4 interface. But for IPv6, every interface has two. In fact, sometimes even more than two, but it always has at least two. Most of the time it has two interfaces. One of them is global IP address, that's the normal one, and the second one is a link local address that is used during Bootstrap but continues for some reason to be used also afterwards. And very often what you find is in routing table, the address that is written for the next hop is the link local address. Because for example, when ED0SWI is sending a packet to this machine, since the two are neighbors, they are on the same link, they are on the same local area network, so they can use link local address. So the link local address of this one is FE80, then lots of zeros, 1, so it can send it to this address here. Same thing on this red network, there are two link local address, FE804 and FE801, but this FE801 is not the same address as this one. Well, it's the same address, but they don't belong to the same interface. The meaning is within the local area network. Right. The next topic is our first example of violation of the TCP-IP architecture. I said at the beginning that TCP/IP is based on a number of principles that are fairly simple, easy to understand, and this will guide us through understanding, debugging, and reasoning about the internet and its protocols. But it would be naive to believe that you apply those principles with the nice layers and everything is done according to that. Because this is done by people like us writing code, right? When you write code, you can do whatever you want. If you are very bad, you do bad things, and if your company is bad, and there are lots of pieces of bad code that are written, and it exists in the world, and we have to live with it. Part of it here is true also in the internet. Here's our first example. The example is called the NAT, Network Address Translation, and it is what we call a middle box. In fact, a middle box is one of the problems of the internet today, is that there's a number of middle boxes, but essentially NATs, that are preventing things to be as nice as they should be. The NATs, like anything that is done in the internet, was developed to solve a problem. It's not just because we had poor people doing bad things. If you do bad things, chances are that in the internet they will not become a standard because you have to go through a standardization process that is called the IETF, Internet Engineering Task Force, where if you invent a NAT, for example, you have to make it to the public, you have to discuss it openly, and everybody can participate in the Internet Engineering Task Force. So if you do bad things, chances are this will not survive this process. So if it survived, it is still causing problems, but there was a good reason. What is the good reason? Well, the good reason is that you don't want Swisscom to have to give you one IP address for each of your devices at home. That was the original idea of the internet. One IP address is one interface is one IP address. So normally, if we use that principle, if I go to Swisscom and I have a computer at home, I want one IP address. Then if I have a printer, I want another IP address for the printer, and if I have a smartphone, I want, etc. So in any decent home, you have easily 10 to 20 addresses because you have all the visitors, the printers, the fridge perhaps, etc. So, and this is not how things are done. Swisscom will give you one IPv4 address. Another reason for giving only one IPv4 address is that there are not so many IPv4 addresses. Very quickly, as the internet became very popular, it grew very, very quickly. and then the number of IPv4 addresses appeared to be too small. So if you ask IPv4 to get not one address but a prefix, like EPFL does, EPFL has, not from Swisscom but from Switch, it has a block of 15 bits. If you ask that, you can, but you will pay, or today you will not get it, but a few years ago you could, but you would pay a large amount of money. Much more than for having a single address. And many companies do the same. If a large company like Nestle has a huge intranet, they don't have one public IP address for each of the machines on their intranet. In fact, they have a few public IP addresses for their servers, for their web servers, for example, and for the gateways to their intranets. And for the rest, most of their addresses are 10 dot something. Now, if you have 10 dot something addresses, if you have private addresses, in principle, you cannot communicate with the outside world. It's not very interesting to be able to communicate only between your PC and your printer, right? You want to go out to the web. How do you do that? Well, you use what is called a network address translation. That is a box that will translate your IP address, which is a private one, to a public one here. Normally, an IP router, as we have seen in many quizzes today, yesterday, and last week, does not do that. The IP address is not changed by an IP router. The address that is changed by an IP router is the MAC address, but the IP address is not changed. So this is not a router, even though very often people are very confusing about the terminology. The name router, for me, when I'm talking in this class, perhaps not outside, but in this class, means an intermediate system of layer 3 of the internet, of IP. That means a box that receives packets, analyzes the IP header, and sends it forward. That's a router. But if you go to Swisscom and you say, I would like your router here, they will sell you a box that does a number of things that does a router. For example, here, in order to interconnect this machine and that one, perhaps you go via a router function, but also does the NAT. So the NAT function is also put in the same box. That's the difference between a function and a box. Functions can be implemented typically as software or hardware that can be implemented in different boxes. And we tend to give the name of the main function to the box. We say, this is a server, this is a router. But inside the box, there are lots of functions. When we do a detailed course like this one, we have to be able to separate the functions. What does it do? Well, the main thing it does is illustrated here. If I have two hosts, A and B, that want to communicate with two other hosts, for example, using Skype. They do audio-video real-time communication. Sometimes we use UDP, sometimes we use TCP, depending, but UDP will be the best in terms of latency. So in this case, we use UDP. UDP, like TCP, uses what is called port numbers. A port number is something that helps you identify which process you are talking to. If I talk to a machine, this machine can be doing typically several things. Very simple machine do one thing, but those are the machines of 30 years ago. The machines of today, they do lots of things. For example, inside your machine, you can have a web server, or a web client, or a DNS server. So in order to know when you send a packet to which application program you have to send it, you have to say to which interface you send it, that's the IP address. And inside the machine, you have to say to which process you send this information. Are you sending it to the DNS server or to the HTTP server, to the web server? You can have both in the same machine. This distinction is done at the transport level by TCP or UDP by using numbers that are called the port numbers. Everybody knows, for example, that the port number that corresponds to web server by default is 80. So if you send to port 80, in principle, this is software, you can always change it, but in principle, it means you're sending to a web server. If you send to port 53, it means you're sending to a DNS server. And the port numbers, they are used as source port and destination port, just the same way as we said before. If I need to talk to some machine, I need to find its IP address, and this machine to whom I'm talking will know my address by looking at the source IP address field. So we do the same for ports. Because in my machine, when I'm talking to a web server, in fact, I may have multiple programs or a single program that has multiple processes that is talking to several servers. So I also need different ports to know when the response will come from a request I've sent, to which part of the software in my machine, to which process typically, or even to which thread inside a process, this information has to go. So we have source and destination port number. So here, when this machine speaks with this guy here, it uses this port number, 1029. And I'm showing an example where this is also using the same port number. It may happen, for example, if you boot A and B, they are exactly the same machine, they run exactly the same code. It's well possible that when they decide to connect via Skype to someone else, the port number that they choose as their local port is the same. And then the IP address that they have is their local IP address. You recognize private addresses. You have the machine 1010 and the machine 1011. Those two guys are each talking to somebody else in the internet. Now, what the NAT will do is it will cheat and change the source. When the packet goes from B to the remote place, it will change the source IP address, which is this one, and will replace it by its public IP address, which is the only address that can be used. Because if someone else wants to Skype me, the only thing they can send traffic to is to my IP address as given by Swisscom. Question? Pardon me?
Your microphone died.
Oh, microphone died. The battery is dead, yes. The other mic is okay? So wireless stuff is beautiful because it saves cabling, but it uses batteries. Voilà. Do you hear me now? Wonderful, thank you. So when a remote correspondent here talks to this guy, they send packet to the IP address of the NAT and to the destination port number, which we'll see is modified here. We could use the same, but we have a problem because the two, if I send to this address and to this port number, I am unable to know which of the two guys I'm talking to. So the trick of the NAT is to use the port number as a way to differentiate between different machines that are seen from the outside world with the same IP address. Question?
Yes. How does the NAT know that the public address is not being used by another program? For example, you said that there are not so many public addresses. So when the NAT is translating to a public address, how does it know that this public address is not being used?
How does the NAT know that this is this address? Well, the NAT is typically your ADSL modem, so it knows it is configured as a NAT. It has one public address. It's called the WAN wide area network port, and it will use the IP address of its wide area network port. So a NAT is a box that has one port which is special. If you take your ADSL modem at home, it has one special Ethernet plug, that's the WAN port, and it has a number of other Ethernet plugs that are for the local area ports. So this is the one port on the right, and there is typically one and only one here. So in that case, you give, it's clear which address it could be used. There are sometimes company NATs. If you do that in a company because you are Nestle and you have 10,000 addresses here, then you have a big NAT that will have not one address, but perhaps a block of with a prefix of 28-bit, perhaps it has 200 or 20 or 30 addresses, then it will pick in round-robin fashion one of the addresses. But let's forget those details. For the time being, what we see is that the NAT does this trick of translating this IP source address and this IP source port number into its own public WAN address and another port number. It has to make sure that there is no collision, and it has to remember in a table here this mapping. So when a packet comes from the outside world to this destination address and this port number, by looking at the port number, the NAT knows this packet is not for me, because you could also speak to the NAT. You can configure it remotely. Swisscom does it for you. They can speak to your NAT. They can download software into your ADSL modem, for example. But it knows from the port number, it's one of the port numbers that is in my NAT table. So I go to the NAT table, and I look at a match, and I find an exact match here, and therefore I translate it into this. So I will modify the IP address and the IP header. Question?
How many port numbers are there?
The port number is coded on 16 bits. So there are 64,000. So the trick is, of course, that you expect that a machine uses much fewer port numbers than possible. It's a trick. Obviously, when you define the size of a port number, you make it such that it's a good match to what people need. And here it's much larger, but the address space is too small, so we use the port number instead of the address space. Question?
And so the NAT assumes that the internet service is available in any ports that it has.
The NAT?
The NAT, that's when it changes the port, it assumes that the internet service is reachable on any ports.
No, we'll see how the question is, how does the NAT chooses those port numbers, for example?
Yeah.
So it keeps a table of all the port numbers it has used. So the only restriction is that it cannot use the same twice.
So the internet service is in so many ports.
For the correspondent host here, this port number, of course, there is a number of reserved port numbers. We'll talk about that when we talk of TCP and UDP. All the port numbers up to 1024, they are reserved. You don't use those. But all the other ones, they are freely usable. So they are allocated by this machine, and they're more or less random. So for the rest of the world, when you talk to this, there is no difference. You cannot know whether you're talking to this machine that has 2 Skype sessions, or whether you're talking to 2 machines, and in fact, there is a NAT in between. Right? This is exactly what happens. So we're fooling the rest of the world here. Of course, the question is how can this mapping be done? I've shown what happens when the mapping is done. How the mapping is done? Well, it's typically done by sniffing, by doing it on the fly. So if B calls someone, for example here, I'm not showing the Skype session, but a web client that goes to a web server. So you're sitting at your computer here, and you send a request to a web server. So this is a public IP address, and this is the port 80 that goes to a web server. So inside your local area network, which may have routed hops here, you end up into the NAT. Now the NAT knows it has to do something because it's a NAT. What will the NAT do? Well, it will create an entry. It will analyze your source port, 1765, and it will allocate to you the next available port in its table. It might be the same if nobody used it before, or it might be a different one. So it will allocate to you another port. So we'll do what is sometimes called label switching. It will transform a port from one value to the other. And it will also remember the address, although in this case, normally it's always the same here. So it will do it when you send the first packet to the web server. And of course, you will typically talk to lots of web servers, so there will be many, many entries for you in the NAT. Right? There will be many TCP connections, there will be many entries, and the entries will stay only for some time. They will be flushed when there is no activity. And when packets are sent over the internet, of course, we change the source IP address and the source port numbers to this one. So again, the web server that is sitting here has the impression, has no mechanism to know whether the machine is behind a NAT, like when we are at home, or not, like when we are at EPFL. And it is the true address of my PC, and this is the true port number that was allocated by the operating system for this transaction. Question? The question is, we do that for IPv4, should we do that for IPv6? The answer is, in theory, no. Because for IPv6, there are so many addresses that you expect that your provider will give you not one IPv6 address, but a prefix. Right? This is in theory, and this is why it's very hard to find good NATs that work for IPv6. In practice, it's not always obvious that the providers will give you complete prefixes. We'll talk about that in a few more minutes, or next week, probably. Normally, with IPv6, the answer is no. Normally, with IPv6, you should receive an entire prefix and use a number of bits for routing inside your house. Right? But there might be good reasons for doing it. For example, if you want to keep all your stuff private, like many companies do. Many companies keep their addresses private, not so much because they don't want to buy IPv4 addresses, but because they really want that their network structure is invisible from the rest of the world. Question? Can you speak louder? I can't hear. Yes, port number has been there since the invention of TCP, which is at the same time as IP. So it's been there from the beginning. For the reason I said before, when you're at the transport layer, when you talk from A to B, you have to know to which part of the code in B you're talking to. There are typically more than one things that can happen in a machine. Yes? Exactly, we'll come to it in a minute. Yeah. This works assuming communication is asymmetric. You have typically you and me at home, and you have web servers that are not behind NATs. Because if the web server is behind a NAT, then, this is my next slide, you have exactly a problem. So if S is behind a NAT, right, so I've done the symmetric here, so then there's a problem. You talk to someone, but this one is not the NAT itself. There's no way to do this. So there is a problem, and this problem was visible in the very early days of internet telephony. Before Skype, there was a Microsoft software that was doing internet telephony, but they could not solve this problem. So typically when A talks to B and you're at home, you're both behind NATs. And you have to know what is the IP address of your ADSL modem, and you have to go into the configure with this software. You have to go and configure. You can manually configure everything. I said is done on the fly. You can of course go into the user guide of your ADSL modem or your NAT, and you can write such an entry manually. Right? And you had to do this for the primitive version of Microsoft Messenger to work. Of course, it was not very successful. Only people who had a PhD in computer science could use it. So the market was not very large. And this is what made, in fact, Skype successful. Skype solved this problem. Right. How did they solve the problem? How would you solve it? Exactly. So you put a server, a Skype server, that is not here for transferring all the audio and video calls, but just for you to communicate, to bootstrap the communication. And this server is not behind a NAT, otherwise, of course, you're there. So what the Skype software does is before calling someone, you call the server and you ask the server, what is under which IP address do I appear, for example. So you can already start having some information. Things are a bit more complicated because not all NATs are doing exactly the things the way they said. Sometimes they do, not all NATs implement the mapping exactly the same way. So you need to test how the NAT is doing, and Skype does all this. It tests all the possible cases. In the worst case, it doesn't work peer-to-peer. You have to go through a Skype server for the communication to happen. In the best case is when the mapping is completely predictable. For example, we use always the same IP address so that the server would see you with the same IP address here. So, but in some cases, it doesn't happen. So if you're interested, there are protocols for talking to servers that will help you discover what are the addresses behind the NAT. That's the price to pay for NATs. Right. Small question. When a NAT has a packet forward, what kind of match does it do? And the correct answer is the majority, B. it does an exact match, which is an essential difference if we think about how IP was conceived. You do longest prefix match, which allows you to have relatively short table for lots of communication. Here, not at all. You need fairly long table, and you need to do an exact match, so it limits the scalability. So if you have a large enterprise that has millions of hosts, you cannot put it behind one NAT. You will need to do a bit smarter solutions. One last question on NAT. Yes?
Can I ask a question?
Yes.
In the example with the Skype, there were two computers. Each one is behind a NAT. And they didn't know IP address of each other. As a result, they connected to a web server, and web server made a relation with them. But as soon as they connect to a web server knows the IP address and port of each of them. And then the web server can say to first client the IP address and port of the second client. And as a result, as soon as connection was established, theoretically, they can communicate not through web server, but directly.
Correct.
So does it happen like this?
Yes, in the best case. If the NAT supports that, it will work in this way. I say in the best case because it means the NAT needs to agree that when it has done a mapping to a destination server and you change the server, this mapping remains valid. Right, which is what I showed on the figure. The mapping is only based on the source. So the Skype server can pass this information to someone else and say, if you want to reach that guy that's behind the NAT, you can use this port number and it will reach this guy. Right? So good NATs accept that, bad NATs don't. Some NATs, they remember the correspondent and they have a more complex association. And if that happens, you're dead. You have to go through the server. And you see the correct answer, which is B for both cases. The NAT is not, in principle, as I said, is not interested in the source port in this direction, but only in the destination port in this direction, which are the port and addresses that correspond to the local area network. Well, that's for the NAT. This is our first example of how we deviate from the nice principles of TCP/IP. We'll see a small number of other ones later. Let's go back to the basic principles. We've been exposed to masks already. So this is a repetition of what we've seen already. In order to work for IP, a host needs to know a number of configuration information. One of them is what subnetwork it belongs to. Why does it need to know that? Well, because of IP principle number one. IP principle number one says, if you want to send a packet to a destination, if it's in the same subnetwork as you should send it directly. If it's not in the same subnetwork, you shouldn't send it to a router. So you need to know two things. You need to know what is my subnetwork? How do I know if another destination is in the subnetwork as me? This is achieved by the network mask. And the other thing you will need to know is what is the address of my router? This is all configuration information that will be needed. So the network mask, as we said last week, for historical reasons, is written in those obscure things. For example, a TPFL is 24 bits typically. In binary, 24 bits gives this. I don't show it in binary. Here I'm showing the ETH mask, which is 26 bits. 26 bits in binary gives this. And if you translate that into dotted decimal, it gives you this mask. So if you visit ETH one day, and you have the curiosity of looking what is your ETH mask, you will see this one. With IPv6, depending on the software, you can use mask notation or simply the length. So here in this interface, which is a Windows interface, it is smarter. It is asking what is the subnet prefix length instead of putting the mask. Some other software, Linux very often, shows off a bit and will put 64 bits equal to 1, which gives all those Fs. This is just one and the same. Right? Some old terminology that's completely obsolete, but you still continue to read it in some documents. The IP address classes. Long ago, well before you were students, for most of you, the addresses, the IP addresses were structured. So we could live without masks in some sense. There were so-called class A address for large networks, class B for medium-sized network, and class C for small networks. And the class C networks are the ones from 192 to 223, the class B from 128. So EPFL was a class B network. IBM 9. Something was a class A network. And the idea is that by looking only at the bits, you could see what is the size of the network. So if I see 9. Something, I know the prefix is 9, at least for routing in the public internet. But this is now obsolete, but people now we can cross boundaries of those blocks. But this is often still found in documents. One last small question. Now only 3 possible choices. I'm showing here a small network. The network has hosts, like A, middle boxes that are Ethernet switches or bridges. We have not discussed in detail what is a bridge. A bridge for us is the same as an Ethernet switch here. And there's a box here that is either a switch or a router. And there are other boxes that we can ignore for the time being. And I'm just asking, what do you think of this address here? The majority says B, which is the correct answer. If we, at least there is a problem, that's what we can say. Because we see the masks here are this. That means 24 bits, the first 3 decimal blocks here. And we see that this is the same local area network, even though it's a bit contorted, but a switch is something that is not a router, so it is in the same local area network. So the IP principle should be that the number, the prefix should be the same for those. Now it's 78 here, it's 77 there, so there is a bug. It will not work if you assign this address. Now perhaps it is those 2 addresses that are wrong, we don't know, but certainly there is a problem somewhere here. So this should be, for example, 78 here. If we assume that the other addresses are correct, the box X should be a router. It cannot be a switch. It is a box that is between 2 subnets here. This illustrates, I mean, this trivial example illustrates one of the issues with IP as opposed to the MAC layer, which is that simple change here of numbering will break the system somewhere. Why will it break? If, for example, host A has a packet to send to a host that is here. This host that is here has the address 77. Something. So host A will say, well, the destination is on the same subnet as me. So I will send directly. So I will send directly to that machine by sending to its MAC address. How do you get the MAC address? We'll see that in a second. And it won't work because this machine is not reachable in the same local area network. So by giving the wrong prefix or the wrong mask, we break communication here. So TCP-IP needs that the addresses and masks are correctly assigned for things to work. That's one of the reasons that the MAC layer is still appreciated today, because the MAC layer doesn't have this problem. We skip this. I'm skipping 1 or 2 quiz. I'll post the solutions later today. The last topic we want to study is how do we communicate directly, and the problem in particular is how do we get the destination MAC address. When you configure an IP host, you must configure its own IP address, its network mask, the IP address of its default router, a few other things, as we will see. But that's all. You configure only information that belongs to the IP layer and to DNS. But you never configure information that corresponds to the MAC layer. Now, when a machine A has a packet to send to something B that is on link with it, it must send it using the local area network, and we've seen that the principle of the local area network is you send to the destination MAC address. So you need to know what is a destination MAC address. And this, you could get it by configuration, but we don't want this because we want everything that's below IP to be completely plug and play. So the problem is how to get this address. This is solved by what is called MAC address resolution. And on Ethernet and on Wi-Fi, it is very simple. A sends a question to everybody on the local area network. A shouts and say, I would like to send a packet to B who has the MAC address of B. This is the principle. This is how it works. It's called address resolution protocol. Let's see in detail how it works with IPv6. With IPv6, the only difficult thing is to know what the acronyms mean. MAC address resolution is part of what is called the NDP, the Neighbor Discovery Protocol. Neighbors in IPv6 terminology means devices that are on the same local area network. Again, there is this vision from IP that the world is a collection of local area networks, and the job of IP is to interconnect them. Let's assume here A wants to send a packet to B, and it knows its IP address, IPv6 address, this one, for example, and I'm showing here the MAC address of B. And because they are configured to be in the same LAN, for example, because the prefix is 64 bits, so they have the same prefix, A thinks that B is in the same LAN because the address has the same prefix. So A will now send a packet asking B, what is your MAC address? Of course, how can you send a packet to someone when you don't know its address? How can you do that? How can A send a packet to B asking B, give me your MAC address? Broadcast, exactly. So the solution is broadcast. You send it to everybody. Now IPv6 does very, very special things. IPv6 does not like broadcast. In IPv4, we'll see we use broadcast. Broadcasts have a very bad reputation. In the past, there were bugs in operating systems that, for example, that generated broadcasts. So they resulted in what is called broadcast storms. So in IPv6, this made some people became very, very nervous about broadcasts, and it has been taboo. So you're not allowed to send any broadcast. So we will find that everywhere in IPv6, broadcast is eliminated. There is no broadcast in IPv6 in practice. And this is part of the complexity of IPv6. I'm not sure it makes a lot of a difference, but this is how IPv6 is. IPv6 will send an IP packet to this address. What is this address? Well, we see FF. That means it's a multicast address. This multicast address is called the solicited node multicast address. It is made by taking the end of the target address. This is the end of the IP address. This is the address of B. We know the IP address of B, but we don't know its MAC address. So I construct a multicast group by taking the last 32 bits of this address, so the last two words, FF661, which is here. The last 24 bits, not 32. So I take 66 and 001. I add this well-known prefix here, and that gives me a multicast group address. That means all machines that have an IP address whose last 24 bits are exactly those ones. Right? This is the meaning of this group. And then I will send to this group. In practice, there's probably only one machine that has this address. There might be several machines, but it will not be a broadcast, so IPv6 is happy. We're not sending it to everyone, but only to the machines that have this address here. And this packet is called a neighbor solicitation packet. It contains a question, so it is an IP packet sent to this address. And inside the IP packet, there is a message, which is not TCP or UDP, but is ICMP, the Internet Control Messaging Protocol, which contains a question, who has this address? So this address is contained in the payload of the packet, not in the destination address. This packet is received by all systems that subscribe to this broadcast group. We will see that in order to receive a multicast packet, not broadcast, multicast. In order to receive a multicast packet, you need to subscribe to the multicast group. And by default, if you own an IPv6 address, you must subscribe to the group of the solicited node multicast address here. So B will receive it. Any sniffer who is cheating might also receive it. There's no authentication at this stage here. B receives it. Question?
B, C, and D have IP addresses, right? IPv6 addresses.
Yes.
So why can't A directly ask that IP, what is your MAC address? Why must it send it?
So the question is, why does A have to ask? Well, in order to talk to someone, you need to use the MAC layer. And when using the MAC layer, you need to create a MAC layer packet that has a destination address with a given MAC address. Okay, that's the way it works. So what thing you could do, you could always use broadcast. You could send IP packets to B by broadcasting them to everyone. You could do that, but we don't like to do that. We don't like broadcast in general. We would like that the packets go only to B. In order for the packets that A is sending to go only to B, A needs to know the MAC address of B. And A doesn't know yet. And we don't want to configure that in A. So that's the goal of this exercise here. A asks to B, asks to everyone who is a member of this multicast group, do you know what is the MAC address that corresponds to this IP address? In principle, only B will get it. It's not impossible that another D has the same final 24 bits. If that happens, D will also receive it. But then D will see, this is not my target IP address. The target IP address is in the payload of the message, in the neighbor solicitation. It is not in the destination address. Question?
Doesn't that create a big security flaw? If I answer with my MAC address, imagine someone asks for my address at the router. I answer with my MAC address first.
Yes. So the question is, does not that create a big security flaw? And the answer is yes. And we'll come back to it in a few slides. Yes, that's one of the problems here on that type of thing. It's completely unsecured. But for most practical purposes, this is what is really happening today on most networks. We'll see that there are ways around that, but this is one of the problems. Then if B, then the end is easy to guess. B gets this message, so B will respond with a response which is called a neighbor advertisement. And then A will know by reading what's inside the packet, here is the MAC address, here it has the MAC address, and from now on, A is able to send packets to B. Of course, you don't do that for every packet. Once you've learned the MAC address of B, you will keep it in a cache, and you will delete it if after, for example, 20 minutes, no traffic has been exchanged. You will delete it and ask it again. Voilà, that's all for today.